Hey everyone, welcome to the latest episode of Mathematics for the Impatient. I'm here with Stan Kladko, who is the co-founder and CTO of SKALE. This is going to be, I think, probably one of my favorite topics so far, because I think it's one of the questions that comes up over and over again. Block time, finality. So Stan, why are these things different? Can you help kind of define them a little bit? Give us the meaning for each of them so that people can understand what block time is and what finality is.
Yeah, that's a great question, Marcus. And I can tell you that things changed. I remember like in 2017, you would try talking to people about block time or finality. People really didn't care. And now you go to any like conference and you go to a party, and like if you want to have a conversation and to create like lots of opposing parties, you just talk about block time and finality. People start talking and explaining things. It's really hard subject. So in general, to understand what block time is and what finality is, the best is to think about the original paper of Satoshi Nakamoto, where he explained Bitcoin. In fact, what's interesting about this paper of Satoshi is that the paper is like 5 pages long. I think it's even like 4 pages long, but has so many different things and so many different ideas. In particular, it actually discusses block time and finality. And the reason for this is that Satoshi Nakamoto had to actually envision everything, and he had to understand all of the major potential problems in order for him to create a system that would work. So let's talk about just the original vision of Bitcoin, or the same as ETH mainnet, Ethereum mainnet. Let's say you have a network, a decentralized network of computers, right? And you can imagine the planet Earth. It's a huge, huge planet. You can imagine these computers being everywhere, like in the States, in Africa, in Europe, all over the planet. And each of those computers is a blockchain node. So basically, all of them have to have the same information. That's what's called consistency, meaning that if you have $10, and if you read one node, it says you have $10, it's better for you to have $10 on all other nodes. They have to be consistent. But the consistency is not so easy to reach because they are geographically distributed. They're talking to each other, they're gossiping, meaning that they're exchanging information, but this information, it lags. There is some time. If something changes in point A, changes will arrive at point B after lag time. So usually there is lots of intermediate inconsistency in the network, and the ideas of Satoshi Nakamoto actually are helping us to actually remove this inconsistency. So now let's imagine this situation. You have a blockchain, and then a blockchain, as the word says, is a sequence of blocks. So if you just say you are in the States and you are at a particular Bitcoin node, what you see sequence of blocks coming to you. It's block number 1, block number 2, block number 3. And in each block, there are some transactions, and you basically execute transactions one after another. So let's say you have $10 and there's a transaction that moves $2 from you to Alice. You would execute this transaction, and then you would have $8 and Alice would have $2, right? So that's basically what's happening for you as a node. You sit, you wait for blocks. For every block that arrives, you actually execute transactions, and you change the amount of money each account has. That's pretty much how blockchain works. Now, let's imagine that you sit in the US and I'm a node in Europe, and you are a node in the US. And let's imagine that there's a ship or whatever that cuts the cable between Europe and the US. So there's no internet connection between the Europe and the US. So the nodes in Europe keep on seeing each other, and the nodes in the US keep on seeing each other, but the network essentially splits. There's this notion of a network split. The network essentially splits in 2 networks. There's not a single Bitcoin network anymore. There are 2 networks because there's no network connection. What's going to happen in this case? You'll be surprised to know that both networks will continue operating, but since they will be disjoint, you could have situations where in the US, you send $2 to Alice, and in the US, in Europe, you send $2 to Bob. Essentially, you can issue contradictory transactions, and because the networks are separated, they will actually not know about that, and they will actually reach contradictory results. So the network in the US will think that Alice got $2, and the network in Europe will think that Bob got $2. Because they don't interact, it will be totally fine. Each node will continue operating. So then let's imagine that someone repairs this cable. Let's say one day passes by, the two networks now disjoint and doing different things, and the counts don't match. And let's say, someone repairs the cable after one day, and the networks actually rejoin. What's going to happen actually, the network is going to heal. But the question becomes, how is the contradiction resolved? Because in Europe, Alice has $2, and in the States, Bob has $2, because two different transactions were executed, and because there was no connection, there was no way to find out about the contradiction. Turns out that Bitcoin has this rule of resolution of contradiction, which will say that the result with more computational power wins. So if the nodes in the States happen to have the total computational power of the nodes in the States is more than the total computational power of the nodes in Europe, after this rejoining and healing of the network, the US nodes will win, meaning that the contradiction will resolve to the US side. And if in the US, Alice was getting $2, Alice will get $2, and Bob won't get $2. So from the point of view of Bob, because Bob is in the minority network, his network has less computational power, things will look like a time machine, like a really, really weird time machine. He will, for one day, like his block explorer, will show that he has $2. And then once the network is healed, he will suddenly see that he doesn't have this $2. So you see the difference between block time and finality, right? In this particular example, the block time is a typical Bitcoin block time, which is like 10 seconds. But in this particular example, the finality is 1 day. Because you literally need to, in this example, wait 1 day until you'll see the real value. So because of this kind of inconsistency of Bitcoin network, the fact that you see things in Block Explorer and you see that you got money doesn't actually mean that you actually will finally get this amount of money when everything is finalized. So then because different people see different things, you may actually be in an environment with less computational power, and you may actually then later have this time machine effect. So then the question becomes, how long do you need to wait on Bitcoin or on Ethereum mainnet to be relatively sure that if you see $1 in Block Explorer, you will actually end up never losing this $1, that the transaction will be final. And it turns out that currently the safest measure is about 40 block times, or about 400 seconds. So on Ethereum or in Bitcoin, the difference between blocks is just like 10 seconds, basically, like on Ethereum. But you have to wait for 400 seconds to be sure that your transaction is final. And the reason for this 400 seconds is because the network is not homogeneous, is geographically distributed, and you have to take into account the effects that you may be in an environment with less computational power. That's number one. And number two, you can also need to take into account the fact that someone may be aggressively attacking the network and having different nodes on the network seeing different things. So not only this can happen randomly or due to some, like someone cutting a cable, but someone may actually exploit the thing and make you believe that you got this $1 or whatever, and then later you will actually find out that you didn't. So because of this nature of Satoshi Nakamoto network, there's this interesting situation which happens that the time machine and healing come to the result that you can actually go back to the past, or you can actually change. You can change because you may end up being in a minority view, and then when the majority view wins and the network rejoins, you may actually change what you see. So that's the basic difference. The reason why finality and block time are so different for Bitcoin and also for Ethereum mainnet.
It's interesting. So part of what you're saying is that block time is one of the things that allows you to understand what your eventual block finality is. But block finality as a consumer is probably the most important thing for you to understand, because that's the moment where you know that your transaction is what it is. So if you have that dollar, you can spend that dollar because you've reached block finality.
Correct. And it's like, when you go to a shop, you give your credit card and, you want to get your Pepsi. And then, the owner of the shop won't give you the Pepsi until she or he knows that you paid, right? So people get very good, understanding of finality. That's pretty much when you're sure you get your money. And because, this feature is not a bug, it's a feature that has been put into the system by Satoshi Nakamoto to create the healing effect for the network. How do you heal a network if it was temporarily split into two networks? So Bitcoin is self-healing. You can cut the cable and then rejoin and it will keep on working. But the mechanism used to heal will actually result in this time machine effect. So, and unfortunately, this means that you have to wait for a long time. So if you want to pay with Ethereum or with Bitcoin and you go to like 7-Eleven, okay, 400 seconds, it's probably not that like the guy who is like in line and waiting, he probably won't be happy if you pay with Bitcoin and Ethereum because you'll have to wait for 400 seconds.
Interesting. So to that point, give us kind of the typical finality and block times for the Ethereum mainnet.
Right, so as we just discussed, the block time for Ethereum mainnet, when Vitalik designed Ethereum, he actually pretty much like put the average block time into the system. It's the constant, and the constant is around 13 seconds. So on Ethereum, if you run your Ethereum node, you'll see every 13 seconds, you will see some other nodes in the network gossiping to you another block, and you will keep on executing those blocks. So the typical block time for Ethereum is 13 seconds, but the typical time for you to wait to be sure that the time machine effect won't happen, for Ethereum, it used to be around 20 blocks. But then there were some hacks done, some attacks done on, not on Ethereum, but on a different network, which is called Ethereum Classic, a less powerful network. And so it's easier for hackers to attack. And actually, it turned out that 20 block time, 20 blocks wasn't enough for finality. So that's why, to be really, really sure, it's now about 40 blocks. So you multiply 40 blocks by like 13 seconds block time, you arrive at like 500, 600 seconds for Ethereum. If you transfer your lifetime savings, it's probably better for you to wait like for 10 minutes, Also, to make sure that, time machine won't actually steal money from you. Right. So that's the typical time for Ethereum mainnet.
Interesting. So then let's kind of course, as we often do, bring this back to SKALE. What are the typical finality and block times for SKALE? And how does SKALE achieve the fast finality that it achieves?
That's a really interesting question. And so SKALE does not use the same algorithm that Satoshi Nakamoto designed. We use a different algorithm, which is called ABBY, or asynchronous binary consensus. Turns out that there's a totally separate branch of mathematics which was developing in parallel, essentially, to Satoshi Nakamoto, and people who were like working on this, they didn't really even care about crypto, or like they were just developing this as an interesting abstract computer science thing. So there was a separate branch of research on consensus algorithms, which are more tightly coupled, but because they are tightly coupled, they finalize much faster. And let me give you an example. So again, coming back to this Bitcoin K example or Ethereum mainnet example, you have the US, you have the Europe, and then someone cuts the cable between the US and Europe, and two networks split. So in case of Satoshi Nakamoto consensus, the two networks will continue like churning blocks, and then once they are reconnected, they will have to heal and repair. In case of the consensus that we use at Scale, if you cut the cable, the networks will just stop. They will temporarily stop and freeze. And because of this stop and freeze feature, they will not create any blocks, and there will be no need for healing. So there's no time machine effect. So these are two very different types of behavior of what happens in case of network split. In case of Satoshi Nakamoto algorithm, they continue working, but then later they have to heal because they work independently, and clearly there could be totally different transactions on each of two networks. In case of our system, the algorithm is tightly coupled, and if the algorithm essentially detects that the network split, then the network will just freeze and wait until the split is resolved, and only after that it will continue churning out blocks. So because of that, there is never a time machine effect, and every block on Scale network, once it's produced, it's already finalized. It's already final. You cannot go back in time and like replace it with a different majority view block that would happen on Bitcoin on ETH mainnet. In our case, when the block is created, it's already final, and because of this, our finality time is actually equal to the block time. So in our case, or I think on our current network, we're seeing block times of around several seconds, maybe 3-4 seconds, and we're actually working to make it faster. In some of our test networks now, for the newer version of Scale, we're seeing block times less than a second. But the point is that it's not only our block time is so fast, but our block time is equal to our finality time. So on Scale, you will be able to pay for your Pepsi at 7-Eleven, and to be sure that people that are like waiting in line then won't say anything bad about you. It will be reasonable for you to do this transaction in Scale because it's fast. And again, the reason why we're able to do it comes from us using algorithms coming from academia. And Satoshi Nakamoto was the first generation of blockchains, and he was great. And in some cases, his algorithm is doing great. But now with newer generation of blockchains, we are able to make things faster. And we're also able to remove this time machine effect that makes things really nasty, that actually you see a transaction happening, and then later you see that it was actually a minority view. And then when the network is healed, you have the majority view, and the transaction actually didn't go through. So because of these two different mechanisms, two different ways to resolve network split, we actually have the finality time equal to the block time. And that's why Scale is really, really useful for in cases when you really need things to happen fast. Like you want to have a game, you want to hold a sword, and you don't want to wait for 400 seconds to get the sword, or in things like NFTs, or in many other things where you want to have interactive behavior. You will actually be able to use blockchains like Scale to have this fast finality.
Yeah, and it's important to understand, back to sort of the time machine effect. A lot can happen in 400 seconds, so you have to roll back a lot of potentially large transactions. So there's some real serious downsides to that approach.
And one of the downsides is also, which due to the time machine effect, every Bitcoin node or every Ethereum node actually does not only store the current state, but stores all of the past states. Imagine you would have a website which wouldn't only store its current design and colors and whatever, but also every design, every way it looked from the beginning of time. Because every Ethereum node or every Bitcoin node at any time needs to go back to the future, so to speak. It needs to go to a different point in time. Keeps on storing lots of information to be able to do it, and this contributes hugely to the growth of storage that Ethereum nodes take. So if a typical Ethereum node now takes terabytes, so you want to run a node, you start download and you wait a week literally just to be able to run a full Ethereum node. One reason for this is because of this time and machine effect that forces you essentially remember everything, and store huge amounts of information.
Very cool. Well, thanks everyone for coming to the latest episode. You can see down below, join us on our Telegram group. We're also pretty active on Discord and Twitter at SKALE Network. Stan, thanks for another great episode.
Thank you, Marcus. It was a really interesting conversation this time.
Cool. Take care, everyone.